predicted is similar with the given rate law equation. So for this part, we will go into that during our face-to-face session on Thursday. Okay. Now let's move to the next part. Okay. So another example, addition of inerts in catalytic reaction. We know that inerts not involved in the reaction. Okay, but some of the inerts, it will absorb on the active side of catalyst. Okay, for example here, okay, Allah. Pointer pen. Okay, for example here we have the reaction of, okay, the first, silap pen lah, pointer. Okay, for the first step, this is the adsorption step, followed with the surface reaction step, and finally the desorption step, because this is the reaction of reactant A to produce product B with surface reaction is rate limiting. Okay, so we know this is the first, this is the surface reaction step where the product form and absorb on the active side of catalyst. So therefore, the first step of reaction, we know that A with the vacant side, and it will absorb to form A dot S. Okay, reversible reaction. So that's why this is the adsorption step, followed with surface reaction step where the product form, and then desorption of the product from the active site and leave the vacant site. And there is another steps of reaction. So if we look at the step of reaction here, the mechanism where the I inert plus S. So we know that this is the adsorption step of inerts, but we know that inerts not involved in the reaction. Okay, then we know that the surface reaction is rate limiting. Automatically, we can predict the overall rate as this equation. Okay, so hari tu saya dah explain the tips on how to predict the rate law and also the mechanism of reaction. So we can write the rate law based on mechanism, tapi usually we will write step by step lah, but we still can predict the final rate law equation as this one. So all the adsorbed species will appear at the denominator, okay, and only the reactant yang appear at the numerator. So therefore only A act as a reactant in this reaction. So that's why KPA here. And all the adsorbed species at the denominator, okay, including the inerts, because inerts also adsorb on the active side, even though inerts not involved in the reaction. Okay, so this is the predicted rate law. Okay, next, if the KIPI value, so meaning that this value is much larger than 1, and also the adsorption rate constant of A and B, so equilibrium rate constant of species A and equilibrium rate constant of species B, okay, reactant and product. Therefore, we can simplify the rate law as this equation. So this is for the case if the concentration of inerts that we use in the reaction is much larger than reactant A. Okay, what we can conclude from this reaction, the rate is reduced by species I, meaning that the rate of reaction is reduced by the inert because of the concentration of inerts in the reaction system is much larger than the reactant A. It shows that the inert can strongly inhibit the reaction of A. So they akan affect the reaction of A because of this value is much larger than another term. Inert blocks the sites on which A must absorb to react and lowers its coverage to a small value, therefore inhibit the reaction. Okay, this is because due to the large concentration of inerts, so most of the inerts will absorb on the active site. Okay, and the absorption of A to the active site and reacted to form a product will be reduced. Okay, that's why rate law decrease, and the inert inhibit the reaction of A to form product B. Next, the effect of temperature. Okay, temperature dependence in surface reaction. So we focus on the surface reaction. Specific reaction rate K will follow an Arrhenius temperature dependence and increase exponentially with temperature. Okay, so this is for rate constants. Okay, kalau you belajar in reaction engineering 1, rate constant increase with the temperature. Okay, but for equilibrium rate constant, it's different. The absorption of all species on the surface is exothermic. The absorption equilibrium constant will decreases as the temperature increase. Okay, based on this equation, so if you compare it with the Arrhenius equation here, Arrhenius equation, there is a negative sign at the activation energy. However, for equilibrium rate constant, there is no negative sign here. So that's why when the temperature increase, the equilibrium rate constant will decrease. So ER, okay, compare for Arrhenius equation, ER is the activation energy for surface reaction. EJ, yakni heat of absorption. So in reaction 1, we write it as a delta H, which is heat of absorption. Okay, so that's the difference between these two equations. So we cannot call this as the Arrhenius equation. This is not the Arrhenius equation because the term here is not the activation energy, but heat of absorption. But we can call it the equilibrium rate constant temperature relation. Okay. Since the rate coefficients are groups of reaction and equilibrium constants, one expect that they are different for different limiting cases. So yang ni kita akan tengok after this. High activation energy implies low rate. Subtracting a heat of absorption will increase the rate considerably. While subtracting heat of absorption in the presence of poison will decrease a rate. So kalau in presence of poisons ni, the concept is similar with in the presence of inerts. Okay, much larger inerts. Okay, and then how we can analyze the temperature dependence on the rate law equation. Okay, for example, this is from the previous example. Overall, a rate law when the surface reaction is limited and the surface reaction is irreversible. Okay, as the temperature increases, Ka and Kb decrease, resulting less coverage of the surface by A and B. So kenapa why Ka and Kb decrease? Okay, from this equation, when the temperature increase, K value here will decrease. So both absorption equilibrium of A and B will decrease. So one is much larger than Ka and Kb. Therefore, at high temperature, the denominator of catalytic rate law approach to 1. Okay, because this term is much smaller than 1. So it can be negligible when the reaction conducted at very high temperature. Okay, and then the catalytic rate law approach to 1. Therefore, overall rate law becomes as this equation. So we can call it this equation as the pseudo-homogeneous rate law first order. Okay. So it will approach to first order reaction. Okay, next, temperature dependence on difference reaction limiting. So kalau contoh ni surface reaction limiting. Okay, this is for surface reaction limiting. Now we look at when the mass transfer limiting, when the pore diffusion limiting, what will happen to the activation energy value. Okay. Limiting rate expression. First, we look at the limiting rate expression before we relate it with the temperature dependence. Okay. When the reaction is limited, meaning that this is for the surface reaction limited. Okay. Rate of catalytic reaction equal to this equation. So, yang ni sebenarnya, so this is the pseudo homogeneous rate. So kita yang ni kita lompat sikit to the next ni. So actually this one is these three equation we call it as a pseudo homogeneous rate. Okay, so that's why R equal to A over V K prime CAB. And actually for reaction limited, the rate reaction equal to K prime CA K double CAB. So this is the reaction limited equation. Okay, and then for external mass transfer pun sama. R equal to R prime KMA CAB. So this is the catalytic rate reaction. But when we transform it into the pseudo-homogeneous rate, dapatlah dalam bentuk macam ni. What is pseudo-homogeneous rate? So after this, I will explain on the pseudo-homogeneous rate. Okay, pore diffusion limited are equal to K prime CAB multiply with the effectiveness factor. So yang ni kita just for FYI sahaja. Okay, so all this equation is for FYI. So what you should know on how to write the rate law equation for these two items. Yang FYI for pore diffusion limiting. Okay, because kita takkan involve the calculation that related to the effectiveness factor. Because we not focus on the calculation part for pore diffusion limited. Okay, we just focus on the surface reaction limited and external mass transfer limited. So actually all this pseudo homogeneous rate becomes from this equation, rate catalytic rate law equation. Okay, then we look at the rate limiting step and temperature dependence. When the reaction is a surface reaction limited, so kalau reaction limited ni sebenarnya surface. Okay, surface reaction limited. So the activation energy remains as E. Okay, the value of reaction, the value of activation energy to remain as E. When the mass transfer limited, the value of activation energy is nearly constant and the temperature also nearly constant. For pore diffusion, the activation energy is half of the value from the surface reaction limited. So macam mana dapat half? So this is the calculation. So this is the derivation to get the value of activation energy when the reaction is pore diffusion is equal to E over 2. So this is the derivation. So this is just for your information. Okay, so this one, actually we relate it with this one, okay, temperature dependence. So if we plot graph, rate reaction, so R here, this is R, y-axis is R, rate of reaction versus temperature. So we want to look at the effect of temperature on the catalytic reaction. Either it is surface reaction limited, pore diffusion limited, and mass transfer limited. Okay, the reaction, so kita tengok dari sini, for this graph dulu kita tengok, actually this log graph tu similar with this graph. Okay, the reaction process goes from reaction limited at low temperature. So low temperature at this point, yang ni. So at this point, at low temperature, the reaction is a surface reaction limited. So yang ni reaction limited. So similar for this one. Sebab graph yang log R versus 1/T ni just actually is similar. So kalau log R versus 1/T at low temperature, this point lah. Okay, at this point. So this is the reaction limited. Kalau reaction versus time versus temperature, so at this point is reaction limited. And when the temperature start to increase, it becomes pore diffusion limiting. So here at this point, from this point to this point, okay, when you look at the reaction rate value, they increase. Okay. So at this point is pore diffusion. Pore diffusion limiting. Okay. And then external at very high temperature, it becomes mass transfer limited. So yang ni mass transfer limited. And if you look at the rate reaction value, dia akan jadi constant. It's nearly to constant. So when mass transfer limited, rate reaction is nearly constant from this point to here. So kalau tengok, if you look at the rate reaction value, it's nearly constant. Okay, so kalau at high rate reaction value, it keep increasing. So at this condition, the reaction is pore diffusion limiting. At low temperature of reaction, the reaction is surface reaction limited. So that's why when the temperature increase, rate reaction increase. So therefore, at that time, surface reaction is much larger than pore diffusion reaction. So that's why pore diffusion limited dekat this point. So yang ni tak ada. Okay, yang ni just we make a comparison in terms of apa tu, the reactant that we use, either it is unimolecular or bimolecular. Bimolecular ni if the reaction involve two reactant. Unimolecular if the reaction involve one reactant. And that actually this table referring to the absorption coverage. Okay, ataupun absorption isotherm. So yang ni only for absorption isotherm. So yeah, ni just focus on absorption steps of reaction, not the overall rate law derivation. Okay, ni tak ada. Okay, next. Macam mana nak stop sharing ni? Okay. Okay, so we are done with the second part. Okay. Now, next we will look at the reactor design. Okay, after we have all the rate law equation, so we need to design the reactor. So how to design the reactor? Okay, share. So part 3, reactor design. Okay, first we look at the rate law equation, the difference between homogeneous reaction and heterogeneous reaction in terms of the units of rate reaction. Okay, so for homogeneous reaction, okay, homogeneous reaction moles per volume per time. So yang ni what you have learned in reaction engineering 1. So the unit of rate reaction is moles per volume per time. Because R equal to K Ca power of alpha. Okay, so the unit of K is depends on the order of reaction. Okay, so that's why rate reaction is equal to moles per volume per time. And then heterogeneous, because it's involved the catalyst, so we need to consider the reaction on the catalyst surface. Therefore, for heterogeneous reaction, usually we will write the rate law based on the rate reaction of moles per area per time. So the area here, area ni where the reaction occur. So the area where the reaction occur meaning that the area of catalytic surface. Or we can measure it as moles per mass time. So mass here is the mass of catalyst that we use for the reaction. Okay, so that's the difference between homogeneous reaction and heterogeneous reaction. And another thing, the volume in homogeneous reaction, the volume here is the mixture, reaction mixture. Mixture of reaction. Okay, not the volume of reactor, but the volume of reaction mixture. Okay, for homogeneous reaction. Okay, heterogeneous reaction, area here is surface area of catalyst. Surface area of catalyst. So that's the difference between homogeneous and heterogeneous reaction. Okay, then how to calculate the actual reactor volume? Okay. Reactor volume equal to volume of fluid plus volume of catalyst. So kalau volume of fluid ni lah yang you kira when you calculate the homogeneous reaction. Yang ni volume of reaction mixture ni meaning that the volume of fluid. Okay. So volume of fluid, volume of your reaction mixture plus volume of catalyst. So if you use a packed bed reactor, okay, let's say this is the packed bed reactor, the reactant, and then product. And inside the reactor, this is a bed of catalyst. So you need to know what is the volume of this bed of catalyst and also the volume of a reaction mixture. So volume of catalyst, here lah, this one lah, this, yang ni. So this is the catalyst that you use. So you should know what is the volume. Barulah you boleh calculate the volume of reactor, VR. Because you know the volume of it and then you know the volume of catalyst. Okay. The pellet is usually porous. So meaning that the palette of catalyst that we use is a porous catalyst, and there is a fluid void space both between catalyst palette and within pellets. So pellet catalyst ni lah yang you arrange it in terms of a bed of catalyst. So the pellet of catalyst, you arrange it as a bed of catalyst. Void fraction, or the fraction of the reactor volume occupied by fluid. So void fraction equal to volume of fluid divide with the volume of reactor. Volume of reactor yang overall ni. Overall tube ataupun overall vessel or cylinder ni. That's the volume of reactor. Okay, including the volume of fluid and volume of catalyst. So the void fraction equal to volume of fluid divide with volume of reactor. Okay, next, space-time. Space-time, there is no different on there's no different from what you have learned previously. So space-time, you can calculate it by volume of fluid in a reactor ataupun volume of reaction mixture divide with volumetric flow rate passes through the reactor. Okay, similar definition. And that for homogeneous reactor, space-time equal to volume of reactor divide with volumetric flow rate. For heterogeneous reactor, we need to include the space void, okay, fraction, void fraction. So epsilon void fraction multiply with the volume of reactor divide with the volumetric flow rate. Okay, V here is volume of reactor, VR. Yang ni pun VR. So tadi sebut-sebut pasal pseudo homogeneous rate. So actually in layman term for pseudo ni maksudnya tipu, not the actual rate of reaction. So pseudo homogeneous rate ni not the actual rate of reaction ataupun rate law equation. So kita panggil pseudo homogeneous rate. So the catalyst is in solid phase with the reactants and product in a gas or liquid phase. Okay, so reactants can be in gas or in liquid. So jangan kata for catalytic reaction only for gas phase reaction. No, for liquid phase also can consider as a heterogeneous catalytic reaction because it will react with the solid catalyst and the solid catalyst remain as a solid. Okay, but if the catalyst, solid catalyst, it can dissolve in the liquid reactant, so yang tu kita tak panggil heterogeneous reaction. Okay, because of the catalyst tu can dissolve in the liquid reactant. So the reaction, we call it as a homogeneous reaction. So you need to differentiate the difference between heterogeneous and homogeneous reaction. Okay, all reaction occurs on the surface of the catalyst. There is no reaction in the fluid phase. Okay, and then the surface reaction rate has the units of mole per unit area of catalyst per unit time, which we will call R. So R prime here, yang ni catalytic rate reaction. And this catalytic rate reaction, if we multiply it with the area of catalyst, surface area of catalyst, so yang ni sama lah dengan yang ni. Okay, catalytic rate reaction multiply with the area of catalyst per volume that occupied by the catalyst. So we will get the rate reaction. So these are, we call it as a pseudo homogeneous rate. Okay. And then surface area of catalyst, sebab kat sini area of catalyst, okay, we can calculate it based on the surface area of, based on the shape of catalyst. So A ni, surface area. Okay, surface area of catalyst, and it is based on the shape of catalyst, based on the shape of catalyst. So it can be spheres catalyst, cylindrical catalyst. So it depends on the shape of catalyst. Okay, similar for the volume. Okay, and then surface area of catalyst also can be calculated based on the ratio of surface area per mass of catalyst. But this one we need to multiply it with the density of catalyst. So yang ni. So for example, packed bed reactor filled with pellet with surface area Sg rho C. So we multiply it, the ratio of surface area per mass ni, we multiply it with the density of catalyst. And the unit is per unit volume of pellet. So this is the unit of Sg rho C ni per unit volume. So this is the unit per unit volume. Right. So area over volume from the previous equation yang ni, A over V also can be calculated by using this formula. Sg rho C multiply with the volume of catalyst divide with volume of reactor, which is equal to 1 minus void fraction. Yang ni. Okay. So actually this equation we derive by relating with the previous ni, yang ni, for heterogeneous catalyst ni. Okay. But usually, okay, so this equation we rarely use. Okay, pseudo homogeneous rate equation yang ni we rarely use, but usually we just use this equation. A over V multiply with the catalytic rate reaction. And it will become as a pseudo homogeneous rate. So highlight kan, this is the useful equation that we usually use to solve the reactor design in catalytic reaction. Okay, so yang ni kita jarang guna. Now, okay, we will look at the mole balance equation and the concept of reactor. Okay. First, we look at the packed bed reactor. Okay, equation, mole balance, mass balance, we look at it later, and the assumption of equation, we will look at it later. So, kita tengok the function of packed bed reactor and the type of packed bed reactor that available in the industry. Okay, most used as an industrial reactor, typically a tank or tube filled with catalyst pellets with reactants entering at the one end and products leaving at the other. Okay, kalau tengok, okay, the first example of so packed bed reactor ni, packed bed reactor is consists of apa tu, yang ni we can call it as plug flow reactor sebenarnya. Okay, plug flow reactor. One of the example of plug flow reactor is packed bed reactor. Okay, so packed bed reactor consists of a bed of catalyst. So yang bulat-bulat ni, the arrangement of catalyst pellets in as a bed of catalyst. So this is the reactant, inlet of reactant, and then product at the outlet. So itu maksud dia, entering at one end and products leaving at the other. So reactant from the bottom, and at the top, product leaving the reactor. And another thing, the catalyst also can be arranged as a multi-tube. Okay, sebab ada banyak tube. So this is tube number 1, number 2, number 3. So the catalyst is arranged in the tube. So we call it as a multi-tube reactor or single tube reactor. Okay, and then Z. What is Z? Z is the length of reactor where the reaction occur. So when we want to determine what is the rate reaction involved in the reaction, so what is the rate reaction value, okay, for this system, we need to consider the length where the reaction occur. So reaction occur, of course lah, starting from the part that consists of catalyst. So that's why Z equal to 0. Z ni equal to the length of catalyst. Z equal to 0 until Z equal to L, the length where the reaction occurs. So the reaction occur from the position of Z equal to 0 until Z equal to L. So this is where the reaction occurs. So similar for packed bed reactor, for multi-tube reactor, for single tube reactor. Okay, reaction will not occur at different part that not consist of catalyst. Okay, and then the fluid flows in the void space around the pellets and reacts on and in the pellets. On and in the pellets ni meaning that the catalyst that we use is porous catalyst. Okay, in the pellet ni meaning that there is a pore diffusion occur. Okay, packed bed reactors, which may be a single bed, many tubes, single bed yang ni lah. So semua ni plug flow reactor ataupun packed bed reactor or PBR. Okay, dua-dua ni boleh. Plug flow reactor or packed bed reactor. But kalau single bed, yang ni lah the first diagram ni. This is single bed. Multi-tube, many tubes, and a single tube filled with catalyst pellet. So yang ni lah single bed. Single bed. Multi-tube reactors allow efficient heat transfer for exothermic or endothermic reaction. So that's the advantage of multi-tube reactor compared to single bed reactor. Okay, then we look at the assumption of reaction. Okay, because the reactor is packed bed, so we assume there is no mixing. Sebab there is no impeller. Okay, tak ada mixer. And the mass balance can be written as this one. U dC over dZ equal to VR. And R here is the homogeneous rate reaction. And usually we can, and actually V ni not a volumetric flow rate pun, but actually the equation U dC over dZ dCA, kalau reactant, if the reactant is concentration of A, only one reactant, so U dCA over dZ equal to rate reaction. And then it's equal to negative R lah, kena ada negative R. And it's equal to dCA over dt equal to negative R. So this is what you have learned in reaction engineering 1. Okay, sebab apa? Because Z over U equal to P. Okay, with Z over U equal to T, residence time. Length divide with U is velocity, okay, is equal to residence time. And then another type of reactor, slurry reactor and fluidized bed reactor. Okay, right, mana equation? Oh, slurry reactor, fluidized bed. Next reactor is slurry reactor and fluidized bed reactor. The fluid and the catalyst are stirred instead of having the catalyst fixed in a bed. So you need to look at the difference. So kalau packed bed reactor, catalyst fixed in a bed. So yang ni PBR, packed bed reactor. Fluid and the catalyst stirred. Kalau dah stirred ni, of course it is similar with CSTR, continuously stirred tank reactor. Okay, so that's the difference between slurry reactor and packed bed reactor. Okay, fluid is a liquid. We call kalau the fluid ataupun your reactants is in liquid phase, you can conduct the reaction in a slurry reactor. Okay, so catalyst pellet or powder is held in a tank through which catalyst flows. The stirring must obviously be fast enough to mix the fluid and particles. To keep the particles from settling out, catalyst particle size in a slurry reactor must be sufficiently small. Okay, so the concept of a slurry reactor ni similar with CSTR. Okay. If the catalyst phase is another liquid that is stirred to maintain high interfacial area for reaction at the interface, we call the reactor an emulsion reactor. But again, the concept still we can assume it's follow the concept of CSTR because of the stirring. Okay, nanti kita tengok how it's look like. Okay, then next kalau ingat, remember, if the fluid is in liquid phase, we use slurry reactor. Okay, if the fluid is in gas phase, we use fluidized bed reactor. So what is what is the reason behind we use fluidized bed reactor? Okay, for if fluid is a gas and we want to react it with the solid catalyst, so it is difficult to stir solid particle and gas mechanically. But this can be simply accomplished by using very small particles and the flowing the gas such that the particles are lifted and gas particles swirl around the reactor. So gas and solid catalyst will swirl around the reactor. So how to accomplish it? So by using small particle and flowing the gas with high velocity gas. So this is how we can swirl the catalyst and the gas reactant around the reactor. So we call this reactor a fluidized bed reactor. Okay, the moving fluid in these reactors is frequently well mixed within the reactor. So the mass balance on the reactor species A is that of a CSTR, meaning that the mass balance for for fluidized bed reactor can be assumed as a CSTR. So similar for slurry reactor ni tadi. So this is how it looks like. Okay, so both slurry reactor and fluidized bed reactor, we assume it is well mixed. So slurry reactor for liquid reactant, fluidized bed reactor for gas reactant. Okay. And the mass balance, so if you look at the mass balance, we can model it as a CSTR. So kalau tengok mass balance is mass balance of CSTR ataupun model as CSTR. Model as CSTR. Packed bed reactor, model as PFR. So yang tadi tu. Okay, yang ni. So it can be model as a PFR. Model as PFR. So that's why rate reaction negative R equal to negative dCA over dt. So yang ni saya tertinggal negatifnya. Negatif. Okay. And that, so slurry reactor left for liquid solid reaction and fluidized bed for well-mixed gas solid reaction. The slurry reactor is generally mixed and is described by CSTR model, while the fluidized bed is described by PFTR or CSTR model. So it depends. So actually, fluidized beds ni depend. Kalau, okay, if the high velocity gas used in fluidized bed, so we can assume, we can model the reactor as CSTR. But if low velocity, sebab it depends on the velocity of gas to to swirl around the mixture of gas and solid tu, is depends on the velocity of gas. Kalau low velocity, we cannot assume it can be modeled as CSTR, but we can model it as a PFR. So, saya tulis kat sini fluidized bed. Fluidized bed yang ni, kalau high velocity of gas, high velocity, model as CSTR. Kalau low velocity Ty of gas, model as PFR. So it depends on the condition of reaction. But slurry reactor, we can model as a CSTR. Okay, because it consists of an impeller. Okay, so it's quite similar with CSTR, okay, for slurry reactor. Except the catalyst, the reactor is for the reaction between the liquid reactant and solid catalyst. So that's why kita tak panggil dia CSTR. We call it slurry reactor. Okay, and then another type of reactor is riser reactor. Okay, riser reactor in which the catalyst is carried with the reactants and separated and returned to the reactor. Dia ada recycle, involve recycle. In this reactor, the flow velocity is so high that the solids are entrained in the flowing fluid and move with nearly the same velocity as the fluid. The solids are then separated from the effluent gases at the top of the reactor by a cyclone. So yang ni cyclone. And the solids are returned to the reactor. So solid catalyst ni return to the reactor. That's why ada recycle kat sini. Okay, recycle of catalyst. The flow profile of this reactor is incompletely mixed. Okay. And in the limit, there is no mixing at all. And you can model the reactor as a PFR. Can be modeled as a PFR. PFTR ni pun sama lah dengan PFR. Plug flow tubular reactor. Okay, which is similar with the previous one. Similar lah dengan packed bed reactor pun. Because we model it as a PFR. Okay. So the flow profile of this reactor is incompletely mixed and ayat yang sama, this repeating. Okay. Thus the riser reactor behave identically to the packed bed reactor with suitable modification of the definition of tau. Okay. So we are done with design, reactor design. So on the application in the calculation, kita akan tengok on Thursday nantilah. Okay. On Thursday we will look at the the application of all the equation. So kita akan tengok dua benda lah on Thursday. First, the example of predicting the mechanism of reaction, and another example ataupun another exercise on designing the reactor. Sempat kot kita buat dapat 3 exercise ataupun 3 question to solve in the class is okay dah. As long as you can understand on how to apply the equation. Alright. Okay, so we are done with the reactor design. And the last part is catalyst deactivation ni kita tengok next week lah. Okay, catalyst deactivation ni tak banyak, just a theoretical part, no calculation involved. So dia senang je. So dia banyak ni je. Theoretical part and to understand how the deactivation reaction can occur. So yang ni kita akan tengok next week. And for chapter, so suppose we start with the new chapter next week. So if we can finish this part, okay, for deactivation, because catalyst deactivation is sikit je, very simple. So we can continue with the new chapter next week. Okay. So yang ni tak banyak. Alright. So for today, I think that's all lah. Okay, sebab kita tak, kalau nak tunjuk example of calculation pun susah sikit. Sebab nak explain, nak tulis tu susah. So nanti kita ni lah ya. And then the video on the example on how to predict the rate law nanti saya update. Ni saya lupa untuk upload dalam MS Team. So nanti bila dah jumpa video example how to predict the rate law equation, how to predict the rate mechanism, how to predict the mechanism based on the rate law. So nanti saya akan update dalam MS Team. Okay, so you need to always refresh your MS Team folder untuk ni topik ni. Okay. Ni apa? Okay, stop sharing. So any question before we end the class? Ada soalan? Tak ada?
Madam.
Ya?
Kiranya kelas Khamis ni face to face lah kan?
Khamis face to face.
Thank you, madam.
Alright. Yang lain ada soalan?
So far tak ada, madam.
Okay.
So far tak ada, madam.
Saya check kedatangan kejap Alright. Simo. Sekejap saya check nama. Okay. So tak ada soalan. That's all for today. Thank you for your time. Assalamualaikum. We meet again on Thursday.
Thank you, madam.
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 Thank you, madam.